Hi guys, Kenna here. Today we're going to go ahead and start taking a look at the ozone layer and the greenhouse effect. Now, if you remember, we talked about the ozone layer once before when we were looking at the layers of the atmosphere. And we've talked about ozone, especially ground level ozone, as a pollutant when we were looking at some of the secondary pollutants that we started looking at in terms of things like smog. Okay, so today, as we go ahead and go through, here are our essential questions. Number one, what is the role of ozone in both the troposphere and stratosphere? Now remember, the troposphere is the sphere that is right here, where you're at right at this very moment. The stratosphere is the next one up, and the stratosphere is the one that contains the ozone layer. We talked about the fact that the ozone layer is super beneficial in the stratosphere because it's what blocks the ultraviolet and X-rays when we go ahead and start thinking about protecting us here on Earth. But when you get that ozone down at the lower levels, it actually becomes a pollutant because it can harm humans, animals, and plants. We'll talk a little bit more about that today. Number two, what causes the hole in the ozone layer and how is it now? When we start thinking about that ozone layer, it may not be as clear in terms of what that looks like. We imagine a layer being something that's solid that kind of goes around the entire way, but in reality, the ozone layer is actually kind of spread out and it's molecules of ozone or O3. And so we need to understand what it looks like, how we started seeing a decline in the thickness of the ozone layer, and where we're at with that at this particular moment. And then number three, is the greenhouse effect good or bad for our planet? And what does it do? Okay. When we think about the greenhouse effect, most people assume that it's negative, but there are some good things about the greenhouse effect. We'll talk about those here today. Lastly, what is a runaway greenhouse effect and how is that related to what we see in Venus? One of the things that we actually have is we already kind of have a model in place for what could happen to Earth over time if our greenhouse effect gets out of control. Because Venus started out very similar to Earth, but now has had so much greenhouse gas trapping of heat that it's hotter than Mercury is, which is the closest planet to the sun. All right, so let's start out by taking a look at ozone. Now, the ozone layer is a colorless gas, mainly found in Earth's stratosphere. It forms a protective layer that absorbs harmful ultraviolet light from the sun. Mostly UVB is what we look at, but it blocks the whole atmosphere, blocks out a lot of the UVC. And then we start looking at the higher level ionizing radiation, X-rays, gamma rays, etc. In 1985, an extreme depletion of the ozone over Antarctica was discovered. This is what they labeled or named the ozone hole. And it soon became really clear that this drop in ozone thickness in the ozone layer was caused by man-made chemicals, particularly a chemical known as CFCs or chlorofluorocarbons. Since then, we've had what we call the Montreal Protocol, and we'll talk a little bit more about this later. And that was an agreement signed by most of the world governments to go ahead and cut back or ban the use of CFCs to help give the ozone layer time to repair. We'll take a look at how that worked and where we're at now. So let's start by looking back and reminding ourselves what ozone is, okay? So the ozone molecule is O3, and remember this is not super stable, okay? Unlike O2, which is oxygen gas that we see in the atmosphere, O3 is actually not that stable, but it actually makes it really good for absorbing these other particles or these rays coming in from space. Most atmospheric ozone is concentrated in that layer that we've been talking about, the ozone layer. And it exists about 9 to 18 miles, 15 to 30 kilometers above the Earth's surface. So remember, we want it up in the stratosphere, not in the troposphere. And when you think about that, you think, oh, is that a ton of different particles like stacked right on top of each other? Well, it actually thins as it goes up and thins as it goes down. So the most dense piece of this is actually in the center, which you'll see in a video here in a second. So ozone is a molecule with 3 oxygen atoms, and at any given time, ozone molecules are constantly being formed and destroyed in the stratosphere. The total amount has remained relatively stable for decades since we've started measuring it. So as we start thinking about ozone, we want to think about the fact that this is an unstable molecule that is a pollutant in the troposphere, but is beneficial to us in the stratosphere. And it's not a tight or dense layer, but in fact, it's a spread out layer, as you'll see here in the video. Okay, so we're going to go ahead and watch this video that's going to go ahead and talk a little bit about our precious ozone layer. And I hope you'll realize, a lot of what I kind of try to bring to these presentations is kind of a perspective other than what you're used to. If you think about it in terms of astronomy and in terms of planetary science and space, you have to remember that space may seem calm, but it's actually a pretty hostile environment, and that our atmosphere is providing a protective layer in many respects for us from space, from the temperature of space, from the radiation from space. And the ozone layer, for example, is really big in terms of helping to protect us from the invisible radiation that is coming in towards our planet. Okay, so space, much closer than you think, and we need to protect the ozone layer because the ozone layer protects us. All right, let's go ahead and take a look at this video.
Space is closer than you think. When you're flying in an airliner at 11 kilometers above sea level, 3/4 of all the air in the atmosphere is beneath you. At just 20 kilometers above sea level, the pressure is so low that water boils at body temperature. Any altitude above 20 kilometers is like being in space as far as the human body is concerned. But the atmosphere extends further, getting thinner and thinner the higher you go. In the upper reaches of the atmosphere, charged particles blown off the surface of the sun smash into widely spaced air molecules, creating spectacular aurora. This is the view from about 400 kilometers up. From here, the atmosphere is just a delicate glow. But this is all there is between us and space. It protects and nurtures all life on the surface. The edge of space is just 100 kilometers above the ground. Rise above this altitude and you're officially an astronaut. 99.99997% of the air in the atmosphere lies below this level. This shows the distribution of ozone in the atmosphere. It is densest at an altitude of about 26 kilometers. If we separated the ozone from the rest of the air and brought it all together at sea level pressure and temperature, it would form a layer just about 3 millimeters thick. But that's not how ozone is found. This is the ozone layer, the diaphanous region of the stratosphere that filters out 99% of the harmful UVB radiation in sunlight. Ozone is continually created and destroyed in the atmosphere as oxygen interacts with UV. It's a dynamic process, but man-made chemicals can break the cycle. If you brought all the air in the atmosphere together, at sea level pressure and 15 degrees centigrade, this is how much there'd be. It would fit in a sphere just 2,000 kilometers across. Within that air, there is about 3 billion tons of ozone, which if you brought it all together, would look like this. All life on Earth relies on this precious gas in the stratosphere. It's potent, but it's vulnerable. It doesn't take much to disrupt the dynamic process of ozone production. CFCs would quickly have depleted our ozone, but the Vienna Convention has saved the ozone layer from destruction. Ongoing stewardship will secure it.
Okay, so as you can see, the ozone is actually more fragile in terms of the layer than you might think. So why do we care about the atmospheric ozone? Remember, ozone in the stratosphere absorbs most of the biologically harmful radiation. Okay, this is the UVB. This is looking at UVC and on up as well. Because of this beneficial role, stratospheric ozone is typically considered to be a good thing. In contrast, if you remember, at the surface in the troposphere, when we have ozone, what we call ground level ozone, this is formed and considered a pollutant. So it's typically bad because it's harmful to humans, plants, and animals. However, it can also be good in some circumstances because the ozone that naturally occurs near the surface in the lower atmosphere can actually help us to remove pollutants that are already there. So it can play a good role, but there's so much of it that's being produced in terms of things like photochemical smog that it ends up being more bad than good in most situations. So once again, ozone in the stratosphere is seen as a good thing because that provides the ozone layer, which protects us from the UVC, UVB radiation coming from space and other ionizing radiation as well. However, ozone in the troposphere is typically seen as bad because it can cause damage to humans, plants, and animals as what we call ground level ozone. Now, there you go. Up on the top, we have our good in the stratosphere. That's the good ozone. And then down there on the bottom, we have our bad ozone, which is typically our ground level ozone. Now, this picture you're seeing here was taken September 9th, 2019, and shows the flight path of an ozone sonde, which is a type of weather balloon that goes up and takes a look at the thickness of the ozone layer. As it rises into the atmosphere above the South Pole here from Amundsen Scott South Pole Station, scientists release these balloon-borne sensors periodically to measure the thickness and protective ozone layer up in the atmosphere. This particular picture was taken by Robert Schwartz from the University of Minnesota. But this is how they actually keep an eye on the thickness of the ozone layer in various different locations around the world. But one of our areas that we highlight is the South Pole because that's where the largest hole in the ozone seems to be. All right. So, what is the hole in the ozone? Following the publication of findings of a British Antarctic survey article in May of 1985, the phenomenon of the ozone depletion over Antarctica is referred to as the ozone hole, first attributed to Nobel Prize winner Sherwood Rowland. The satellite image, which I'll show you here in a minute, of the ozone hole has become a global symbol of this environmental threat and really helped to mobilize public support for the Montreal Protocol, which again, I'll go on here in a second. This has been one of the more successful areas of environmental activism where the sharing of the ozone hole image, the satellite image, really mobilized populations of the world to go ahead and accept regulation. And as it accepted regulation, we were able to come to consensus and actually start limiting, even banning the use of CFCs, which were the primary molecule that scientists found to be responsible for the depletion of the ozone layer. And it helped to solve the global depletion of ozone. The international community regulated CFC production and consumption by adopting the Montreal Protocol in 1987. That's just 2 years. It's a lot quicker than what we've seen when we go ahead and start taking a look at climate change, for example. Now, again, CFCs were probably the primary component, but we also have nitrous oxides, which we've talked about before with respect to smog, as well as producing that ground level ozone we were discussing before. These are dangerous substances because just one molecule of nitrous oxide or CFC can break down over 100,000 ozone molecules. Remember that O3 is very unstable. Okay. If we break down the ozone, it's not going to be able to absorb the ultraviolet light in a meaningful way. And so that's not going to help protect us where we're at. Ozone levels over the northern hemisphere where we live have been dropping by about 4% per decade. So it's not that it's not affecting us here. It's just not creating as big a hole as what we see over the Antarctic. Okay. Decreased ozone levels can lead to the holes that we currently have today, and they're not always in one place. Okay. Those holes can move around even though we've had the larger hole in the ozone layer over the Antarctic for quite some time. Now, here is the picture, and this is an older picture, and I'll show you here in a little bit some other images so that you can kind of get a better idea of what it's done since then. But a NASA satellite photograph of the South Pole taken October 15th, 1967 shows what was the most serious hole in the ozone layer. And you can see it here in the pink. Okay. So right here over Antarctica, and it's pretty small at this point. You're going to see when you get to 2019, 2020, that we have a lot bigger hole that's there now. But there's a victory here, and we'll talk a little bit more about that when we get there. That comes in the form of the Montreal Protocol. The work of atmospheric scientists and environmental researchers continues to play a large role in informing the policymaking under the Montreal Protocol. What is the Montreal Protocol, you might ask? It's an international treaty designed to protect the ozone layer by phasing out the production of numerous substances, at the top of the list being CFCs. It was agreed upon in September 16th of 1987 and entered into enforcement of it, at least, on January 1st of 1989. So starting in 1989, it's been in place to try and reduce CFCs and other molecules. Now, it's had some revisions. It wasn't perfect at first day, as most regulations aren't, but through use of it and increased activity from many of the governments in terms of looking at the success and what they could do to try and limit it, we end up seeing revisions in 1990, 91, 92, 93, 95, 97, 98, 99, and even 2016. Because evidence was suggesting that the ozone hole in Antarctica is slowly recovering because it wasn't growing at the same rate that it was when it was first identified. Climate projections indicate that the ozone layer should return to 1980 levels by about the year 2050 or 2070. Okay. Now, that may seem like a long way out to you, but I hope you realize that this is using the Earth's natural processes to go ahead and recover. And they are not fast processes. But again, if we can leave the planet alone, it should be able to go ahead and heal itself, just like we talked about in other instances. Now, due to widespread adoption and implementation, this has largely been hailed as one of the greatest successful international cooperation efforts. And Kofi Annan was quoted as saying that perhaps this is the single most successful international agreement to date. In comparison, effective burden sharing and solution proposals mitigating regional conflicts of interest have been among the success factors for ozone depletion challenge. Most countries have effectively banned any form of CFCs. Okay. This is something that, like the Kyoto Protocol, which we may have heard of more in the news more recently, has really failed to do. So in this case, with ozone depletion, there is global regulation already being installed before we'd even come to a scientific consensus. When we go ahead and start looking at the science for things like climate change, scientists agree. We know where we're at. We know where we're going. If we can just get everybody to buy in to the steps that need to be taken to make this work, like we did for the Montreal Protocol to limit the CFCs for protecting the ozone layer, we should be in pretty good shape. So public opinion is going to be part of what needs to change if we're going to go ahead and be convinced of the imminent risk of climate change and what we need to do in terms of changing it. So what are some of the things that are depleting the ozone today? Because even though we've really gotten rid of typical CFCs, it's not that there aren't things out there that are still impacting the ozone layer. We've got aerosols, sterilants, carbon tetrachloride, foams, halons, HCFCs, which is related, and actually most countries are now limiting the use of HCFCs too. Okay, methyl bromide, solvents, coatings, adhesives. Like there's a lot of different things that we're looking at in terms of what could damage, and some of them are bad. Think about our nitrous oxides. 100,000 ozone molecules can be damaged by just one of these CFCs or nitrous oxides. So something to kind of keep in the back of your mind. Now, this diagram just kind of goes through that process. So let's say a CFC is released into the environment by industries, and then that rises up into the stratosphere. In the stratosphere, the sunlight breaks the CFCs up and releases the chlorine off it. That chlorine then ends up destroying ozone. And as it destroys the ozone, when it interacts with it, more and more reactions, it's a chain reaction, which ends up breaking down many ozone molecules into the oxygen. So I have a little video here kind of showing you where the hole in the ozone is. Different color used this time than the image I showed you before. But this actually talks about how much the different weather patterns and the wind in particular is going to go ahead and relate to our holes in the ozone layer. Okay.
This year, the ozone hole over Antarctica was far smaller than expected. In fact, it was the smallest since the ozone hole was discovered, the result of unusual weather patterns in the stratosphere over the South Pole. The ozone hole is caused by interactions between chlorine from chemicals called chlorofluorocarbons, or CFCs, and ozone. Although CFCs were banned by the Montreal Protocol in 1987, they last a long time in the atmosphere. Ozone depletion is enhanced when temperatures are colder, so the ozone hole fluctuates with the season, appearing during the colder austral winter months and disappearing by summer. It reaches an annual maximum size in early southern spring, usually in October. This year, the polar vortex, a spiraling wind pattern over the South Pole, was unusually wonky. This warmed the stratosphere, the part of the atmosphere with the ozone layer, which significantly slowed down ozone depletion. Although the small ozone hole this year was caused by weather patterns, the ozone layer has shown overall signs of improvement as a result of the Montreal Protocol. NASA and NOAA have worked together to study the ozone hole since its discovery.
Okay, so as you look at that, that's really looking at 2019. Now, unfortunately, since that time, we've actually seen some increases, and actually, one of the largest ones was actually in 2020. So, when we go ahead and start thinking about this is not something that just goes and is done, but it's going to fluctuate because those HCFCs and other CFCs that are in the atmosphere are going to react with the ozone layer at different times. And the weather is going to dictate that and how fast they come up into the stratosphere. And all of these factors are going to impact what the hole in the ozone is. And remember, we talked about if we're really looking at healing, we're talking about this being in about 2050 or even up to 2070 when we actually start seeing most of the hole being gone. So we still got another, a good 30 years before on the early side, we really start seeing a massive improvements in the ozone density. But the progress, the stabilization, the fact that we had the smallest in 2019 that we'd seen since the first measurements back in the 60s, that's pretty impressive. Okay, considering we went through the 80s, which was a time of excess, as we mentioned before. Okay, so here's where we are. Where are we at with these CFCs, HCFCs, etc., and now the new HFCs? HFCs, which are still in use, we don't use the CFCs or the HCFCs the way we used to, but they're still used in refrigerators and air conditioning systems, and their use is actually on the rise. They replaced the ozone depleting substances phased out from the Montreal Protocol, and about 1.6 billion air conditioning units will be installed worldwide by 2050, making the problem even worse. Now, this is not as bad as the CFCs or HCFCs, but this is definitely contributing to damage of the ozone layer. Luckily, sustainable and energy efficient alternatives are now being made available, including natural refrigerants, so we don't have to use chemicals like each in the HFCs. Okay. An ambitious agreement to reduce HFCs use via the Montreal Protocol can avoid 100 billion tons of CO2 by 2050 and up to half a degree of warming by 2100. Now, we'll talk a little later on about the 2-degree Celsius number and about 1.5 and where we're at. We mentioned it briefly last class, but I want you to kind of keep in mind that everything that we decide to go ahead and do to try and make lives better for us here, we have to think about the long-term effects and the side effects, the things that we don't necessarily think of as being a primary outcome, but they definitely impact what we're talking about. Okay, so we've talked about the ozone layer. I think you guys have a pretty good idea of what it does, how it works, and how we're damaging it, and how we're hopefully fixing it. Now I'd like to kind of switch gears and take a look at Earth's greenhouse effect. Did you ever wonder why the Earth is the only planet in our solar system that contains life on the scale that it does? Well, the main reason for that is that Earth lives in what has been called the Goldilocks zone, like the story of Goldilocks and the Three Bears. Goldilocks she wanted the one that was just right, not too hot, not too cold. And in fact, that's what Earth is. And the nice thing about this is this means that Earth's temperatures remain within a pretty stable range that happens to be suitable for life, largely because our atmosphere is naturally insulating. Right? So let's explore a little bit more of the greenhouse effect, understand where it is, where it's headed, and what the future of that looks like. So first, let's answer what is the greenhouse effect? Well, the Earth actually behaves very much like the glass of a greenhouse, keeping in just the right amount of heat and letting out what it doesn't need. First identified by scientists back about 1896, the greenhouse effect is the natural warming of the Earth that results when gases in the atmosphere trap heat from the sun that would otherwise escape into space. So you can see in the diagram on the left, the sun's rays come in, and when they go ahead and hit various factors or the ground or the water inside the atmosphere, you can see that it hits aerosols and other gases, it reflects. Now, when it does that or is released back into the atmosphere, most of that actually gets captured, okay? But some of that gets leaked back out into space, and that helps to regulate and maintain a fairly constant temperature. Now, it's the sunlight that makes our Earth habitable. We can only live here because of the solar energy coming to us from the sun. And while 30% of that solar energy that gets to our world is reflected back into space, about 70% passes through the atmosphere to the Earth's surface. Here, we absorb that, and it's absorbed by either land or oceans or atmosphere, and then it heats the planet up. This heat then gets radiated back up in the form of invisible infrared light. Remember, infrared is going to be one of those non-ionizing forms of radiation. And while some of this continues on into space, the vast majority of it, about 90%, as I mentioned before, gets absorbed by the atmospheric gases, known as greenhouse gases, and redirected back towards our planet, causing further warming. Now, if the level of greenhouse gases stays constant, our planet's temperature stays constant because it keeps trapping the same amount. But if we increase the greenhouse gases, more of that heat gets captured and the average global temperature rises. And this is what we'll talk about as we get more into climate change. So what are these greenhouse gases we're talking about? Well, some of them are going to be there naturally, and it's not that they shouldn't be, but maybe the quantity or location of them is not where it should be. In the Earth's atmosphere, the dominant heat absorbing gases are one, water vapor. It's part of our water cycle. Two, carbon dioxide. But remember, when we start looking at the makeup of our atmosphere, most of it's nitrogen gas, followed by oxygen, and then a bunch of others, CO2 being up at the top. But ozone and water vapor are actually pretty low in terms of percentage quantity for our atmosphere. So these gases, again, if you remember the diagram from the previous slide, let the sunlight in, but only a little of that energy back out. We do have some other greenhouse gases that are causing extra trapping of this in our atmosphere and leading to the increase in overall climate temperature. So these include methane. Again, large contributor to the methane is going to be our production of beef and feedlots. We have nitrous oxide and CFCs, which we were talking just a minute ago about. These all absorb significant amount of heat and may be part of the reason for global warming on its current trajectory. Okay, so again, greenhouse gases let the sunlight in, but trap some of that heat in the atmosphere. Okay. Now, how much greenhouse gas are we talking about here? For most of the past 800,000 years or so, much longer than human civilization has existed as we know it, the concentration of greenhouse gases in our atmosphere is somewhere between 200 and 280 parts per million, or ppm. Okay. So there were somewhere between 200 and 280 molecules of the gas for every million molecules of air. But if you can take a look at the graph here on the right, once you get past, what is that, 16, 17, 18, 1900, really, you start seeing it rise, and not just a little bit, it's pretty dramatic. Okay, when you go ahead and get to 2000, those numbers are really quite high, especially when we start looking at CO2 and methane. Okay. So, what happens then? What does the future look like if we continue to pump greenhouse gases into the atmosphere? Well, for comparison, let's go ahead and take a look at the planet Venus. It turns out that Earth isn't the only one with a greenhouse effect. The greenhouse effect on Venus, however, keeps its surface temperature about 470 degrees Celsius. For reference temp, Earth's average temperature is about 14 degrees Celsius. Why is the greenhouse effect on Venus so much stronger than what we see on Earth? Okay. So let's go back to Earth, return to Earth for a minute. In the past century, the concentration of greenhouse gases had jumped from about 250 parts per million, like we were talking about, to over 400 parts per million. Almost all of that driven by human activities, primarily fossil fuel burning and deforestation. The higher concentrations of greenhouse gases, especially CO2 in particular, is causing extra heat to be trapped and global temperatures to rise. So what we're seeing is that Earth's greenhouse gases of today are looking increasingly like those that would have been what we saw on Venus. Okay. Now, what we're trying to avoid by the Montreal Protocol, by trying to go ahead and limit the amount of these greenhouse gases in the atmosphere, is we're trying to avoid a runaway greenhouse effect. A runaway greenhouse effect occurs when a planet's atmosphere contains greenhouse gases in an amount sufficient to block thermal radiation from leaving the planet, so extra heating, and ultimately preventing the planet from cooling down and having liquid water on its surface. Now, remember, when scientists are looking for life on other planets, one of the key things they look for is a solvent or a liquid that can allow life molecules to do chemical reactions. On Earth, this has been water. And so water has long been something that we look for when we look for life on other planets. If you can't have liquid water, those chemical reactions that we rely so heavily on aren't available. Okay. So Venus is the hottest planet in our solar system, even though it's not as close to the sun as Mercury is because of this greenhouse effect. And in fact, if you want to think about it in terms of Fahrenheit instead of terms of Celsius, the average temperature on the surface of Venus is 847 degrees Fahrenheit. Now, I don't know about you, but to me, that doesn't sound very comfortable in terms of living conditions. Venus has a very thick, toxic atmosphere filled with CO2, and it's perpetually shrouded in really thick yellowish clouds full of sulfuric acid, and it traps a ton of heat. And this is what causes the runaway greenhouse effect on Venus. Okay. But if we're not careful in terms of what we release into the atmosphere as far as pollution is concerned, if we're not careful in terms of protecting ourselves by keeping the ozone layer intact, there is every potential that Earth could begin to barrel down this pathway that makes it much more like Venus, which does not sound like the kind of place I personally would like to live. Okay. So on the left here, you can see the natural greenhouse effect. Sunlight comes in, we get the solar radiation, we've got some greenhouse gases. After they get absorbed, they're re-released back out. Some of that gets captured back into the planet again for warming, and some of it gets moved into space to help keep our temperature pretty constant. However, with human enhanced greenhouse effects, because of more greenhouse gases, You have the same amount of radiation coming in, the same amount of radiation being re-radiated, but more of that is being recaptured and less is being emitted back out into space, causing our average global temperature to increase. So this is what we talk about in terms of greenhouse gas emissions and global climate change. Okay. The last thing I really want to talk about and what I'm going to leave you with today is where do these greenhouse gas emissions that humans produce from human activity come from? Okay. Well, the first real place we start looking is from electricity and heat production. Okay. And this is all going to vary depending on where you're coming from. When we go ahead and start thinking, do you live in Beijing? Do you live in South Africa? Do you live in heavily populated areas? What's the size and level of the economy? What is the average lifestyle of the person that lives? There's a lot of factors that impact where we get our greenhouse gas emissions from. But so we're going to look at the current numbers in terms of where they're coming from on our planet today, but this is going to vary a little bit from country to country. Let's start with electricity and heat production. Okay. The burning of coal, oil, natural gas, all the fossil fuels that we've been discussing so far this term are largely used to produce electricity and heat, and this accounts for 1/4 of the worldwide human-driven emissions, making it the single largest source in most cases. In the United States, it's second largest, as you can see in the diagram here. In the United States, it's behind transportation and responsible for about 27.5% of US emissions in 2017. Most of that coming in the form of carbon dioxide as the primary gas released, along with small amounts of methane and nitrous oxide, mostly again from coal combustion. The next one on the list here is agriculture and land use changes. Okay. About another quarter of greenhouse gas emissions come from agriculture and other land use activities, deforestation being a big one as part of this category as well. In the United States, agricultural activities, primarily raising livestock and crops for food, account for about 8.5% of greenhouse gas emissions in 2017. Of those, the vast majority are methane, primarily from manure decomposition, and as beef and dairy cows belch and pass gas. Okay, with some nitrous oxides being released from nitrogen-heavy fertilizers in the plant growing process. Trees, plants, and soil absorb carbon dioxide from the air, but unfortunately, forests are being cut down in many cases. And while reforestation is happening, it's not at a rate that's going to replenish what we're losing in terms of carbon capture. And we'll talk more about this as we get into climate change in some later lessons. So the plants and trees do most of this carbon capture via the process of photosynthesis by converting carbon dioxide into glucose. But the soil also has all these microbes and carbon binds in them. So non-agricultural land use changes, especially deforestation, reforestation, and afforestation, can increase the amount of carbon capture or the amount of carbon in the atmosphere, depending on what we're doing with that particular swath of land. In the United States, land use activities currently represent a net carbon sink, absorbing more carbon dioxide than they emit. This is part of why we need to protect our forests, our national parks, to keep the carbon that we have in the ground. Okay. Next on the list is industry. About 1/5 of global human-driven emissions come from this sector, which includes the manufacturing of goods and raw materials, cement and steel being two of the biggest offenders, food processing, construction, and in 2017, it accounted for about 22.5% of US man-made emissions. The majority of which, again, is carbon dioxide, although we also have methane, nitrous oxides, and some fluorinated gases. The next one is transportation. The burning of fossil fuels, namely gasoline and diesel, power the world's transportation sector to the amount of about 15% of global greenhouse gas emissions. In the US, Americans buy bigger cars and drive more than most places on the planet. We also take more plane flights than most other countries do. And as a result, this accounts in the United States for about 28.7% of US emissions in 2017. So we do a lot more polluting through transportation than most other countries do. And this actually ends up being our largest sector, as I think I've mentioned once or twice before. Okay. In total, if you include this with agriculture and electricity, we have a problem in terms of pollution that is based on the systems that we have in place for consumption. As far as transportation is concerned, nationwide, cars and trucks are responsible for over 80% of transportation related carbon emissions. So that's literally on our shoulders because we're the ones driving most of those vehicles. Only about 20% comes from airplanes, boats, these types of things. Okay. The next on the list is buildings. Operating buildings around the world generates about 6.5% of global greenhouse gases. In the US, homes and businesses account for about 11% of warming emissions. These emissions are again mostly made up of carbon dioxide and methane, mostly from natural gas and oil for heating and cooking, though we do have some sources including managed waste and wastewater and leaking refrigerants from air conditioners and refrigerators, things like that. The last category we take a look at here is other sources because we can't cover everything here. But this category includes emissions from other things, including some energy related activities that are not fossil fuel combustion, extraction, refining processes. When we start looking at those things that lower the net energy of our fossil fuels in terms of what they produce. Globally, this sector accounts for about 9.5, a little over 9.5% of emissions. So that gives you an idea of what we're looking at in terms of human greenhouse gas emissions and where they come from. We don't want them to get out of control. We don't want to end up with a runaway greenhouse effect. We don't want to end up having Earth looking more like Venus. So we need to make sure that we protect our atmosphere in terms of the greenhouse gases. We want to protect our atmosphere in terms of the ozone layer, so that we can have a long-term successful plan for being on this planet and hopefully for many, many more years without some sort of catastrophe as this gets worse. Okay, that's what I've got for you guys today. I hope you have a great rest of your day. Take care of yourselves, stay healthy, stay safe, and I'll talk to you soon. Take care. Bye-bye.